So let me get recording. Okay, cool. All right. So what I want to do is I want to go over problem number 1 because I think it's really, you could learn all these formulas, you could do all that stuff, but until you actually do the problem, you're kind of like, how the hell am I supposed to use this stuff? So I just want to bring up something that I brought up in the video, and that's this ASD method. And ASD, again, is one of 2 methods that are used in structural engineering to determine what the size of your beam has to be. It's really, that's what it is. It's a process by which you go through, and it's kind of like a school of thought in terms of if you make these steps, you can select a beam. ASD is used for steel, LRFD is used for concrete, and then both are used interchangeably for wood. So what is the process with ASD? It's, let me jump to it. It's basically this. You select your beam based on the bending moment. Then you check it against shear strength. You check it against deflection. And if it passes all 3 tests, then your beam is good. If it fails any one of the tests against shear strength or deflection, then you have to go over it all over again. So what I'm going to do is the following. I'm going to go ahead and today, I'm going to go ahead and solve the whole interior beam for you. Your responsibility is to solve the exterior beam, the girder on column line 3, and the girder on column line 5. Hopefully you also realize the fact that there's a difference between each of those 4 conditions. The beams are the ones that are running horizontal. The girders are the ones that are running vertical. The beams rest on the girders, and the interior beams carry the tributary width. So very similar to what we did in the last assignment. The interior beams carry this tributary width. The exterior beams only carry that tributary width. So it's a lot less. In terms of the girder is going to carry all 3 of the beams on each side of it, but the exterior ones are only carrying that much load, right? So there's an inherent difference between all 4, all right? So what I want to do is I want to go ahead and solve this problem. So why don't we look at a couple of pieces of information based on, so we always want to define our knowns. So I'm going to go ahead and switch to my document camera, but I'm going to read it out loud as I do it first. If I try to solve for the interior beam, what I know, my knowns, and this is true for all the problems, is that dead load is equal to 50 PSF. I also know, let's see, live load is equal to 100 PSF, and they determine that based on code. And FY, which I'm going to get into, is equal to 50,000 PSI. I also know that it supports a plaster ceiling. And I know that E is equal to, what is it, 29 million PSI. Okay, now that I know everything, it's going to tell me a step-by-step process by which to solve it. But at this point, what I'm going to do is I'm going to solve the beam. All right, so what I'm going to do is I'm going to share my screen for my document camera. It's going to show a chair. I switch, there we go. All right, so hopefully you have something like this. I'll put this thing on this side so hopefully people can see. All right, how do you go about it? All right, so can you guys give me a thumbs up that's on video? Can you see my hand right now on the page? Okay, cool. All right, so let's get going. The first thought about it is, and now I'm gonna solve number 1, right? So I'm just listing my knowns. Even though these knowns are true for everything, I'm not gonna relist it every time, but I listed it my first time. Now what I'm gonna do is I'm gonna calculate the loading. So what does it mean to calculate the loading, right? And you don't have to write this specific thing, but what I'm trying to get to is I'm trying to get from PSF to PLF. That's my goal, all right? That's what it means to calculate the load on the beam itself. So what I'm gonna do is I'm gonna go ahead and I'm gonna do it step by step, just so that it's more clear, so that somebody doesn't look at these values and is like, how did you get that? I want to solve for, so I have PSF, I want to get to PLF. So what I'm going to do is, what I know about the interior beam is that there's a couple things. I'll draw a quick picture of an interior beam, right? I know its length is 18 feet. If you look at your document, you know the beam is 18 feet. Now, I also need to determine the tributary width of the beam. So when I look at my problem, and I'm actually going to switch back to that screen. Let's go with this one. Which screen is it? I don't even know. This one? Sure. Okay, when we look at this problem, one of the things we see is, since I'm solving an interior beam, the beam is 18 feet, but what is the tributary width of that beam? Well, I need to look here, right, to notice the dimensions. So can somebody unmute and tell me what's the tributary width of an interior beam? Anyone?
9.
Okay, so where did you get 9 from, Emma?
I thought I remember you saying it's half of the width.
So tributary width, you got to remember, is the amount of load that it's carrying from the floor above. So this beam right here, what area or what length is it responsible for carrying? So when we think of tributary width, so yeah, thank you for responding, Emma. And I think that that's something that we got to be aware of. It's half of this, but it's also half of this. This tributary width is this. For the exterior beam, it's responsible for carrying this. So what would be the tributary width of an interior beam? Anyone out
18?
there? Huh? Say it again.
18?
Okay, so the 18 is the length of the beam, but what we're trying to determine specifically is what is this, right?
Isn't
What
it 6 feet and 8 inches?
exactly right. Because, oh, whoops, wrong annotation. Because of this dimension here, it's carrying 6'8", because this whole thing is 6'8". So let me go back to what I meant, Emma, when I said half. I'm glad you're thinking of the half, because you're right on point. It's carrying half the weight on this side and half the weight on this side. So it's really 3 feet 4 inches on this side, 3 feet 4 inches on this side. So this beam right here is carrying 3 feet 4 inches, 3 feet 4 inches, for a total of 6 feet 8 inches.
Oh, okay.
Exterior beam, its tributary width is only gonna be 3 feet 4 inches. Okay. All right. So now that I got that much, whoops, I didn't mean to annotate. New screen. Okay. So, oh, not the right one. There we go. Okay. So we know that this is 6 feet 8 inches. So what I'm going to do now is, if I want to go from PSF to PLF, it means that every square foot, right now it's carrying 50 PSF of dead load every square foot, and it's carrying 100 pounds of weight every square foot. So, you know, obviously I could do this a lot faster. So I'm just going to do that for the sake of this class. Normally I'd break it up, but I'm going to say the W of dead load plus live load, meaning the load, right? Because load is considered in PLF. The W of dead load plus live load is equal to, well, it's the 50 PSF plus the 100 PSF times tributary width. So W is equal to basically the PSF times tributary width. So then in this situation, the tributary width is 6, and I'm going to make it a decimal. 6, 8 is, let's see, 8 divided by 12, that's 2/3, so 6.67. And actually, oops, I should have put units, 6.67 feet. So that's going to mean 150 pounds per square foot times 6.67 feet. And that's going to end up giving me 150 times 6.67, 1,000.5. One of the feets cancel out, pounds per foot, which is PLF. All right. So, any questions so far? Questions, preguntas so far? Okay. All right. So let's get going. So I calculated the load now. Now I can create the beam diagram. All right. Well, if I know it's being loaded with this much weight and that this is a distributed load, right? It's uniformly distributed. Then what I can do is I can say, hey, this beam is being, so this 18-foot beam, right? It's 18 from here to here, is being loaded along the entire length of the beam with 1,000.5 pounds per foot. I want to solve the end reactions. So my goal when I calculate the beam diagram is to know what is RA and RB. Is there a fast way to calculate RA and RB? So from our previous lesson, how could we solve this quickly, right? Because right now, in 2 lessons ago, we learned about the static equilibrium equations, but in this last equation, we learned, hey, there's a much faster way. There's a shortcut method. The shortcut method tells us that RA is equal to RB, which is equal to WL over 2. We also learned that the shortcut formula tells us that the max moment is equal to WL squared over 8. Someone might ask, where do I find these? Go to 3.23, right? This is what we did in the last assignment. We could use static equilibrium equations, completely valid, or we could just do it this faster way. I'm gonna plug and chug. I get, I think I'm gonna round a little. I did this calculation earlier. It's 9,000. Maybe I didn't round, I don't know. Yeah, I did round. It's technically 9,004.5. I'm rounding, okay? Just throwing it out there. I'm gonna go ahead and plug and chug. As I know someone's gonna give me a hard time for that too. All right, why are you rounding now? You round at the end. I know. Okay, I'm gonna round again. Yes, I know. I'm rounding. So what I'm gonna do is I'm gonna round to, I'm just gonna keep the numbers nice. All right. Foot, pounds. Yeah, pounds, feet, wins out in the numerator. Yeah, foot pounds. And that makes sense. It's moment. All right. So far, any questions? I'm gonna stop each way. All right. Let's keep going. So this is my beam diagram. This is my end reactions, which means that this is 9,000 pounds and this is 9,000 pounds. All right. This is my max moment right here. Now, what the question asked me is, now we're going to get into it, right? So far, we've actually done nothing new. And someone's all like, oh, I'm already lost. All right. What the ASD method asks us is, you are going to use the end reaction forces and the moment to calculate a nominal moment. All right. Well, what does nominal moment mean again? So I'm going to write the formula. All right. So I'm going to calculate the nominal moment. Nominal moment. The formula says that Mn must be greater or equal than Ma times safety factor B, and that's an epsilon, okay? Or no, that's an omega. Sorry, that's omega. So what the formula tells us is the following. It tells us that the safe load of a beam, all right, what's considered safe for a beam, the nominal moment, should be greater than the moment that is developed through the loading condition times a factor. Because this nominal moment should not be less than the safety factor times the load condition that is possible on this building, because that would be terrible. And we always put safety factors because honestly, you never know when people are going to exceed the expected values. So what we do is we kind of boost it up for worst case scenario with a safety factor. And specifically, the ASD method tells us that the safety factor should equal 1.67 for moment. So what the formula is telling me is that, hey, just FYI, your nominal moment better be greater or equal to the amount of load that's actually on the building, which is the amount of moment created by the building, which is that 40,500 foot-pounds. I'm just plugging and chugging, times the 1.67. So what it's telling me is that nominal moment must be greater or equal to, and again, you guys are gonna be mad at me because I'm rounding ahead of time, and yes, I know, I just did it kind of quickly, so I had to do it ahead of time. 67,635 foot-pounds. Someone's gonna say my value is slightly different. I didn't round. Yes, you're right. You're a better structural engineer. I know I'm breaking the rules a little, but I'm gonna move forward because I don't want to recalculate it. So what this tells me is, hey, your beam that you're selecting better be greater, better be able to carry more than 67,000 foot-pounds of moment. And if your beam doesn't, then you picked the wrong beam. So what we're going to do is we're going to use the nominal moment in order to select a beam, because that's our like first baseline check. It better pass the nominal moment check. So how do we determine what the strength, the bending strength of a beam actually is? Well, it tells us that the nominal moment is equal to Fy times Zx. Now, any questions so far? Can you guys unmute yourself? I'll give you guys like 10 seconds. Anything that you guys want to look at right now? Anything?
No.
No, Jacob, you're good?
Yeah, I'm good.
Okay, all right, I'm gonna move on. So now what we gotta do is, what we wanna be sure about is the fact that the nominal moment of the beam we select is greater than this. And this is how we're gonna check, hey, what is the nominal moment of a beam? So the reason why we're gonna do this is because we're kind of doing it backwards. We're saying, well, if we want this portion to be greater than that, right? Then why don't we just substitute this in its place? So what I want then is, I want this product to be greater than this. So why don't I just substitute Fy times Zx must be greater or equal to 67,635 foot-pounds. Because I know if the product of my beam is greater than that, I'm good. But I know this value is given to me. And just to kind of jump back into POE, Fy is the yield stress of steel. or of any product. But Fy means what is the yield stress of the material you're using. If you remember back to stress, the yield point is the yield stress if you go onto the y-axis. So when I used to look at stress over strain, the graph would look something like that. The yield point is right here. So what the Fy is basically saying, hey, what's the stress at the point of failure? And it was given to me. So actually I'm going to solve for Zx. Zx must be greater or equal to 67,635 foot-pounds divided by Fy, because all I did was I divided Fy on both sides. So I'm going to say divided by Fy. This was given in the problem. What is the tensile strength, the yield strength of steel? So based on the givens, what's the yield strength of steel? So I'm going to ask the group, can you guys look at your givens? What is the yield stress of steel?
Is it the 29 million PSI?
That's modulus of elasticity. So look back at your givens. What's the yield stress of steel? And you got to understand
50,000 psi?
exactly 50,000 psi, which means that if I'm looking at my graph, this point right here is 50,000. It means that at the yield point, the stress is 50,000 for steel. It doesn't mean it's the ultimate. It doesn't mean it's the failure stress. It means it's the yield point, and that's what we consider failure. So I'm going to replace this with 50,000. So I'm going to say 67,635 foot-pounds divided by 50,000 pounds per square inch. Okay. The pounds will cancel themselves out. But now I'm left with inches in the denominator and feet in the numerator. So that creates a problem for me because I'm not working with the same units. So I'm actually gonna kind of jump into the next page a little, but leave this up here so I can slide down. Right now, what I gotta do is, so I'll rewrite this actually, 67,635 foot-pounds divided by 50,000 pounds per square inch. My pounds already reduced to 0. Because this is in the denominator of a denominator, we know it's going to move up there. But now I'm dealing with feet and inches squared. So I'm going to convert the numerator to inches. So 12 inches, 1 foot. The feet reduce. I'm going to calculate this entire problem out. So 67,635 times 12 divided by 50,000. My units are going to be inches cubed. I multiply that out and I get 16.2. If you're using exact values, technically you will get something slightly different. And again, this goes back to the whole fact of I shouldn't be using rounded values, but I did. Okay. Any questions up to this point?
Do you want us to round our values too?
No, you guys can follow along with me. Just realize that if you go back and you plug in some of these exact values, you may be curious as to why I have slightly different values than what it shows on your calculator. And that's because I just looked at my calculator and wrote a simple value to move forward. Just so that I didn't have like decimals and stuff like that. It's not a good practice. I just did it. Because, yeah. Okay, any questions other than this so far? Okay, so what did we solve for? What we said is that Zx better be greater or equal to 16.2. Why did we solve for plastic modulus? That's what this is. It's called the plastic modulus because that's going to allow us to select a beam. So this is where the chart comes into play. So what I'm going to do is I'm going to share my screen again. All right. if I click on this link, it takes me to this website. From this website, I'm gonna go ahead and select steel sections. It's the second link down, steel sections. I don't think this is necessarily intuitive, which is why I said this lesson is really important, and I'm giving you guys extended time to do this assignment. But we use W beams in America. It's just the most common type of beam used in the US is W beams. Other countries will use other types of beams. So I'm gonna select the W beam. It looks like an eye. It looks like this, okay? This is called a wide flange beam, and it looks like an eye. Sometimes people will call it I-beams. Sometimes people will call it wide flange beams, whichever you're right in terms of whatever you call it. You'll notice that there's two tabs, the dimensions and the properties. As mentioned in the video, the reason why we call it W10 by, let's just go to the very bottom. The reason why I call it something like W10 by 19 is because it's nominally, like roughly 10 inches tall, and it weighs, where's the nominal weight? It weighs, oh great, I gotta go all the way to the bottom now. What did I select, 10 by 19? There it is, 19 pounds per foot, which really means it's how thick it is. So the goal of this is to find a ZX that is greater than 16.2. Well, someone would say like, wow, does that mean I have every single beam to select? Yeah, essentially you could. I mean, I could select a W14 by 82 because, hey, the ZX is greater than 16.2, but that doesn't make sense. So what we're gonna do is we're gonna look at a couple of different beams that have different depths. So the very first beam that is greater than 16.2 that I see on here on the 10 range is a 10 by 17. So I'm gonna mark that. I'm gonna say that the 10 by 17 is an option, okay? It's an option because ZX is greater than 16.2. The 10 by 15 is not. Now I'm gonna go past the 10s and I'm gonna jump into the 12s. So which 12 works? Well, the 12 by 14 works because it's 17.4. I'm gonna jump into the 14s. The 14s, the 14 by 22 works. And I could keep doing this, right? There's gonna be a 16, there's gonna be, you know, there's gonna be an 18 that works, there's gonna be a 21 that works. So now, which one should I select? Should I go with the 10 by 17, the 12 by 14, or the 14 by 22? Of those three options I just listed, which is the best option and why? So I want you guys to think about that. And if anyone feels comfortable enough to answer, give it a shot. I love that you guys are trying. You know, that's the main, that's the goal, right? Which of those three, 10 by 17, 12 by 14, or 14 by 22, which one should I select?
12 by 14.
Why do you say that?
Because it's like the closest one.
Okay, that's definitely one option. It's the closest one to the ZX. That's a good answer. Other reasons, and actually you're absolutely right. It is the 12 by 14, but not for that reason.
Like maybe it's more cost effective as well.
Ooh,
Since
you're exactly right. Why is it more cost effective?
you're not like using as much like per.
It has something to do with the second number. 10 by 17, 12 by 14, 14 by 22. What does the second number mean?
It's shorter.
No, actually, the 12 is actually technically taller, right? Because the first number, the 10 is the height, the 12 is the height, the 14 is the height. That's the what we call the depth, but by depth they mean, you know, the height of it on a cross section. So what does that second number mean? And thank you, Emma, for your responses. I appreciate it. Anyone else on this group right here? Come on, folks, jump on in. What does the second number mean on a W beam?
The second number means its weight.
Exactly right. So why would I select a 12 by 14 versus a 10 by 17 or a 14 by 22?
Well, because it weighs less and you don't want so much weight put onto the rest of the beams.
Exactly. Not only is it going to weigh more, which is going to make it now less stable, right? Well, you're adding more dead load, but technically you're using more steel, because just because something's taller doesn't mean it's heavier, right? We see that all the time. You can have a short, stubby person and a tall, thin person. Just because they're taller doesn't mean they're heavier, right? And that's exactly the case with the 12 by 14. It's taller than the 10 by 17, but it's thinner. And so inherently, it adds less weight to the building and is using less resources, which potentially means it's cheaper. So now, before we leave this page right here, I want to go ahead and write a couple things about the 12 by 14. On my paper, and I'm going to switch to it, I'm going to write a couple things. First, I want to confirm, I'm going to select the 12 by 14. My selection is 12 by 14. And the truth is that I don't know if this is actually going to work or not. It's just the first check. It passes the nominal bending moment. I still have to check it against shear. I still have to check it against deflection. So what I'm going to do is I'm going to write some properties of the 12 by 14. I'm going to write the fact that its ZX is 17.4 inches cubed. And I got that by going right here and writing this number right here. I also want to know its moment of inertia. In the last question, some folks asked, how do I calculate the moment of inertia? It's like, no, don't worry about that yet. They were trying to ask, how do I solve deflection? Do I have to solve for E and I? And I said, no, don't worry about that yet. You're going to learn that the next assignment. The I is right here. It's 88.6, which means that this specific beam, its moment of inertia along the x-axis is 88.6 inches to the fourth power. I also want to know some other properties about it. I want to know TW and depth. So those don't happen to be on this tab. So I have to scroll all the way to the top, go to the dimensions, and the number I want to know is the depth for a 12 by 14. So I'm going to go find the 12 by 14. It's right there. The depth is 11.91. And the TW is equal to 0.2. I've got all the information I need. I'm going to switch back to my other screen. Okay. I'm going to move this to the side. Okay. Any questions so far? All right, I'm going to try to move through this next section a little quicker because I don't want to take forever. All right. So now, what is the next check? So ASD tells us the following. Solve for nominal moment. Based on ZX, select beam. Then check it against shear. Then check it against deflection. If no, then select beam. Just kind of like a flow chart. If it passed if you're selecting the beam based on nominal moment, you know it already passed this. So now we selected a beam. Now I'm going to check it against shear and see if it passes on to the next phase, which is deflection. If it doesn't pass these tests, then I have to select a new beam. All right. So what it tells me is ASD tells me that the nominal moment better be greater than the shear that the beam is going to experience times a safety factor of shear. That safety factor of shear given by ASD method is 1.5, which means the maximum shear that the beam is going to experience based on the load conditions times 1.5. Whatever beam you select better be at least this value. Okay. So now, why don't we determine what the maximum shear that the beam can experience? Well, the end reactions are the maximum shear. So if I go back to my beam diagram, this was the shear of the beam. So I'm going to plug that in. And then I'm going to multiply it by the safety factor. It tells me that the maximum shear better not be greater than 13,500 pounds. Now, it's telling me that the beam better be able to withstand a minimum of this. So now we have to calculate what the beam can actually withstand. So based on the 12 by 14 beam that we selected, we know that the maximum shear, the nominal shear that the beam can actually withstand, is 0.6 times Fy times AW. This is a formula that's given. This is the max shear that the beam can nominally experience while still being safe. AW is equal to D times TW. So I'm going to rewrite this formula as 0.6 times Fy times D times TW. And I'm going to plug in chug. 0.6, 50,000 pounds per inch squared times 11.91 inches times 0.2 inches. I got this from the properties of the beam. It's right here. So that's why I wrote it down, because I knew I was going to need it. Then I go ahead and say that equals 71,460 pounds. Is the 12 by 14 beam okay? So is it a good beam or is it a bad beam? Did it pass the first check? What do you guys think? Or do you guys have questions? Crickets. At least give me some indication. Go off mute and tell me, are you following along so far? Does this make sense? Not everyone at once.
Yes.
Okay, thank you, Brianna. I appreciate it. A simple yes is all that I'm looking for, folks. Okay. I will move on. So this is what the 12 by 14 beam can withstand while still being safe. Is it greater than the shear that the loading condition gave us? Well, yeah, I mean, 71,000 is greater than 13.5. So really quickly, I mean, 71,460 does happen to be greater or equal to 13,500 pounds. So far, you've passed the tests. So now I got to check it against deflection. Now, this is the part that's going to be, if you haven't gotten confused yet, then I want to make sure to walk through this, okay? Code tells us that the maximum deflection that is allowed on a beam, when you add the dead load and the live load, that should be less than or equal to L over 240. This is straight from the code book. It also tells us that the maximum deflection for just the live load should be L over 360. So what I'm going to do is I'm going to say 18 feet, which is the length of the beam, divided by 240. But I'm going to convert the feet to inches. I'm going to convert the feet to inches again. And I'm going to calculate this. This gives me 0.9 inches. This gives me 0.6 inches. This is not the actual deflection the beam is going under. This is what code allows. It says, hey, and actually this formula, just to be clear, is when I have a plaster ceiling. So what it's asking me to do is it's basically saying, hey, if I have a plaster ceiling, this is the maximum amount of deflection that your beam can withstand given this type of load condition. before it's considered too much deflection. So now what we got to do is we got to check what the actual deflection of a 12 by 14 beam is given the load conditions. So this is where MD solids really comes into play. If I had MD solids, I could just run the beam condition under MD solids. I could check for the deflection. I could update E&I, and there's a way I can show you. Or I could do calculations, which is the longer way. But because some of you don't have MD solids and SkyCiv doesn't do deflections for free, I'm going to calculate the actual deflection. If you looked at 323, there was a formula. And that formula said deflection is equal to 5W L to the fourth divided by 384 EI. You probably looked at that formula and you're like, wow, that's a lot of big numbers or that stuff. I'll deal with that some other time because Mr. Menjivar didn't ask me to do it for this one. Well, now you are. So what's the actual deflection based on dead load and live load? Well, it's 5 times 1,000.5 pounds per foot. That's what W is. Times 18 feet to the fourth power divided by 384 times 29 million pounds per square inch times I, which if I go back to my properties of the beam, is 88.6. It's right there. 88.6 inches to the fourth. Now, because this 18 is in feet, I really should do this. I'm going to go ahead and multiply it times 12 inches over 1 foot, then raise it to the fourth power. And you guys can do this on your own calculators. And let me be clear, this fluctuates dependent on the beam you choose. When I plug this in, I get 0.79 inches. What did code allow for my deflection to be, though? So can you guys unmute yourselves? What did code allow my deflection to be? I think I'm talking to myself at this point. You guys can unmute yourself. What did code allow my deflection to be?
The deflection could be anything less than or equal to 0.79 inches.
So that's so this right here is the actual deflection. So what did the code allow?
Oh, 0.9 inches.
Exactly. Am I good?
Yes.
Okay, for this one I am, but I got to check it against this one. And this is where you guys aren't going to like me, because all I'm going to do is I'm going to check it against live load. Sorry, that does a crossing off. The deflection of the live load. So I'm going to plug and chug the exact same values. If you guys are good with calculators, you'll realize that all I have to do is update this portion. Someone's going to say, where does the 667 come from? That comes from, yeah, and this gets a little more complicated. The live load is 100 PSF times 6.67. Okay, so times 18 feet, you know, multiplied by 12 inches over 1 foot to the fourth power over 384, 29 million, 88.6. What is this? To the fourth power. And I get 0.52 inches. Oh, wait. Shoot. I screwed up. I was looking at the wrong one. I only messed up on this last part, not the whole thing. Don't worry. Oh, I know where I messed up. Okay. Hopefully you guys are with me, okay? This actually was equal to 0.92 inches, okay? So this was 0.92 inches. So was the 12 by 14 beam adequate?
No.
No, unfortunately it was not. So the 12 by 14 beam had a greater deflection than what code allows. Damn. So all I got to do, and it's not that hard because all I got to do now is I got to do the following. I have to now select a different beam. I could go back to my other two options I wrote. When we were doing this, I said maybe there's a 10 by 17, there's a 14 by 22, but there's one other option. I had originally selected the 12 by 14, but now the 12 by 14 is not adequate. Why? Because the 0.92 is actually greater than what code allows me to deflect. So instead, what I'm going to do is instead of choosing one of these two, I'm going to step up the 12 to 16 because now this is still lighter than that. And the properties of the 12 by 16 are the fact that the Zx is equal to 20.1 inches cubed, and the moment of inertia is 103 inches to the fourth power. So that's the properties of the 12 by 16. Instead of having to plug and chug all these values in all over again, all I'm going to do is I'm going to update the 88.6 and I'm going to plug in 103. So essentially what happened right now is I checked it against shear, it passed. I'm going to check it against deflection, both dead load plus live load and the live load deflections. And if no, select new beam. So I did. I selected a new beam. I updated the I values. So this is going to be 103 inches to the fourth now. And what I'm going to end up getting is this is where the 0.79 came from. So the 0.79 is for the 12 by 16. The 0.52 is the deflection of just the live load for the 12 by 16. It passed both checks. Someone would say, do I have to check it against shear? If you go up in sizing of a 12 beam, you don't. If I selected a 10 by 17 or a 14 by 22, you would have to check it against shear. But because I just stepped up in this realm, I don't have to check it. I don't have to check against shear. And now the 12 by 16 passed both deflection tests because it is smaller than what code allows me, which is 0.9 and 0.6. And because it passed both, my final beam selection is a 12 by 16. And that's my answer. Okay. So I didn't get much feedback from the group while I was talking. And I'm sure people were writing, trying to catch up and stuff like that. So I'm sure there's reasons for it. But now that my lesson is done, I wanted to see what kind of questions you guys had, or if you want me to reiterate certain pages, certain portions, times you got lost.
No, it all made
At
sense.
the end, it got a little confusing there. Okay, group, this tells me everyone understands. I don't know if I'm missing something. I don't see anything on the chat group. Okay, folks, questions.
Can I just ask a general question?
Yeah.
Are we still having spring break, or will that be integrated into phase 2?
Yeah, we're still having spring break as far as I understand.
Okay. Because I was looking at the calendar and I just realized that we were actually supposed to have a 2-week spring break. Pretty funny.
No, what do you mean? What calendar?
Yeah, on the DUSD calendar, they updated it. It's kind of weird. It might have been a mistake, but yeah.
For this year?
Yeah, it was kind of weird when I saw it too.
Where did you find that calendar?
On Downey Unified.
It's possible that they're looking at future years. Like this year, our spring break is 13th, 17th. Unless they like have a new phase. I don't know. Maybe they released the.
They probably modified it to adjust to phase 2. They were probably expecting for us to like be in here until like late April, so they just But yeah, I just had that questions.
Okay, yeah, I could look into it. I'm not 100% sure. Then my understanding is we just still had 1 week.
Okay, thank you.
Yeah, questions on the assignment though. Questions on 324. Questions on 324. None. Okay, so I'm gonna release a help video for the exterior, and so I did the interior beam, but what I'm gonna do is I'm gonna say the following, and this is gonna give you a starting point for the next ones. Let me share my screen. Okay, do you guys see the assignment screen right now? Can somebody give me a quick?
Yeah.
Okay, so conceptually, the thought is the same. The only difference is that for the exterior beams, the tributary width is not going to be 6.67, but 3 feet 4 inches. So the process by which you're going to go about it is going to be exactly the same. I'm going to release a help video for the girders, but the difference between the girders and the beams is the following. Let me annotate it. When we drew the load condition for the beams, we drew a distributed load and it looked like this. And that makes sense because it has tributary width either here or here. But the girder doesn't have tributary width. The beam condition and the beam diagram for the girder looks like this. I'll draw it like this so that you guys can see it. This girder right here has, let me erase that. This girder here has a beam there. Sorry, I gotta erase that. Still learning. A beam there, a beam there, and a beam there, a beam there, there, and then obviously it's not equal out, it's not uniformly drawn, but a beam there and there. Where did those 4 beams come from? Well, there's one beam resting on it here, another beam resting on it here, another beam resting on it here, and a beam resting here. So this girder is experiencing a different condition on each side of it. So what's going to end up happening is that the beam is resting on the girder. So when I draw my girder load condition, it's going to look like this. Instead of a distributed load, it's going to be 4 point loads. Instead of being a distributed load, because this is a distributed load, right? This is like one of those where it's W. This is 4 point loads. So instead what's going to happen is this is going to be P you know, P, P, and P. These are 4 point loads that are on the object itself. So instead of there being 4 or a uniform load, there's actually a distributed load across the entire beam itself. This one, the girders are going to have 4 point loads, and the point loads are going to be the end reaction forces of the beams themselves. Because you got to think about the fact that the girder itself is supporting the beam by how much reaction force? Well, if the beam is pushing down with 9,000 pounds, then the girder itself is pushing up with 9,000 pounds. So each point load is 9,000 for each beam that is touching it. So if I'm dealing with girder line 3, then P is equal to 18,000. But if I'm dealing with girder column line 5, then the P is equal to 9,000 because it's only going to experience 9,000 pounds of reaction force because it's only experiencing one side of it. So the load condition is a little different. So I'll release a video on that, but you know, if you guys have questions on this, this is like the hardest conceptual assignment of the year. I know we're at home and stuff like that, but you really got to catch up with me because this is type of stuff that, and I do want to help you guys understand that this is actually like second year engineering calculations, second or third year. If you plan to go into civil, mechanical, anything like that, this is, you're definitely doing college level structural engineering calculations here. So, you know, it's not supposed to be easy the first time, but I'm going to support you through the process. So make sure you ask questions, okay? Dylan, I will check up on why that's the case, okay? I'll grant you access if not. Any other questions though before I stop this? Okay, folks, I'm gonna end the recording.